Welcome back to another training video using the UK Electrical Simulator. In this video, we're going to look at the different charging stages used by a solar charge controller when charging a battery. We'll explain what happens during bulk, absorption and float, and how the controller changes the voltage and current as the battery becomes more fully charged. When charging a battery, the solar charge controller does not just push power into the battery at one fixed rate. It normally works through a number of charging stages. In the bulk stage, the controller delivers as much current as it safely can, and the battery voltage rises. In the absorption stage, the controller holds the battery at a set charging voltage, while the current gradually reduces. Once the battery is fully charged, the controller moves into float, where it lowers the voltage and simply maintains the battery without overcharging it. On the workspace, we have 6 solar panels connected to a solar charge controller, feeding a 48-volt 300 amp-hour battery. The battery is currently at a low state of charge, so this is a good point to demonstrate the charging process. When we switch on the solar charge controller, it starts in the bulk charging stage. At this point, the battery is low, so it can accept a higher charging current. The controller is charging the battery with around 20 amps of current. If we increase the sun slider to 100%, the solar panels can produce more power, and the charging current increases to around 40 amps. In the simulator, the charging process has been speeded up so that we can clearly see the battery state of charge changing. In the real world, charging a battery from a low state of charge to full could take several hours, depending on the size of the battery bank, the amount of solar power available, the charge controller settings, and also the loads connected to the system. So as the battery charges, its voltage rises. This is because the battery is moving from a discharged state towards a fully charged state. At the start, the battery voltage is lower, so there is a larger difference between the charging voltage and the battery voltage. That larger voltage difference allows more current to flow into the battery. We can link this to Ohm's law, where current depends on voltage and resistance. A simple way to think about this is the charging current equals the difference between the charger voltage and the battery voltage, divided by the resistance in the charging path. So when the battery voltage is lower, the voltage difference is larger and more current can flow. As the battery voltage rises closer to the controller's target charging voltage, the voltage difference becomes smaller and the charging current naturally reduces. This is why during the charging process, we see the battery voltage increase while the charging current starts to reduce. In the simulator, the values are updated as the state of charge increases, so we can see the voltage gradually rising and the current gradually reducing. Once the battery reaches the controller's absorption voltage, the charge controller moves into the absorption stage. During absorption, the controller holds the battery at a controlled voltage. The battery is still charging, but because it is now much closer to full, it accepts less current and the current begins to taper down. So bulk charging is mainly about getting a large amount of energy back into the battery, whereas absorption is about completing the charge in a controlled way. The controller prevents the voltage from rising too high while allowing the current to fall as the battery becomes full. Once the charging current has reduced to a low level, or once the absorption time is completed, the controller moves into the float stage. In float, the controller lowers the voltage to a safer maintenance level. The battery is no longer being heavily charged. Instead, the controller provides just enough current to keep the battery topped up and to supply small standing loads. In the simulator, we have kept this process simple so that it is easier to understand. The voltage rises towards the charging voltage, and once the battery reaches full charge, the current is reduced to around 1 amp to show the float or maintenance condition. In the real world, the exact voltages, currents, absorption time and float behaviour depend on the battery type and the settings programmed into the charge controller. The controller will remain in this maintenance state until the battery is used again and the state of charge drops. In this simulator, once the battery drops below a set value, such as 97% state of charge, the controller returns to bulk charging and starts charging at higher power again, depending on the amount of solar energy available. However, in real systems, this return point can usually be adjusted, so not every charge controller will behave in exactly the same way. Now let's look at what happens when the system has a load connected. Here we have an inverter charger feeding a 230-volt AC load. The inverter takes DC power from the battery and converts it into AC power for the load. If the load is drawing more power than the solar panels can provide, the extra energy has to come from the battery. When that happens, the battery starts to discharge. If the battery continues to discharge and reaches a low state of charge, the inverter will eventually stop inverting to protect the battery. In this simulator, the inverter stops when the battery reaches around 10% state of charge. It then moves into an idle state. Once the battery has had a chance to recharge, the inverter will restart when the state of charge reaches a higher value, such as 15%. Again, in the real world, these settings can be different. The low voltage cutoff, restart voltage, charge current, absorption and float voltages, plus the various battery protection settings, all depend on the type of battery, the inverter, the charge controller, and the manufacturer's instructions. So, to summarize, bulk is the main charging stage, where the controller delivers a high current and the battery voltage rises. Absorption is the finishing stage, where the controller holds the voltage steady and the current gradually reduces. Float is the maintenance stage, where the controller lowers the voltage and keeps the battery topped up without overcharging it. Understanding these stages is important because batteries are not all charged in exactly the same way. I hope you've enjoyed this video looking at the different charging stages used by a solar charge controller, including bulk, absorption, and float. In the next video, we'll look more closely at the different battery types, including lead-acid, lithium iron phosphate, and sodium-ion batteries, and why using the correct charge settings is so important. Please like, subscribe, and leave a comment below.